And welcome to this webinar, which is the third organized by the Bamboo Project, which is a project, as you might know, which is funded by the European Union. We will hear more about it later. Its aim, in short, is to make heavy industry more sustainable through a number of new technologies that we are exploring in this webinar series. Today's topic is combustion monitoring in the steel industry using computer vision and machine learning. So it's quite an exciting topic because we are going to speak about artificial intelligence. So first of all, let's go through a couple of rules. Please keep your microphones and cameras switched off, and maybe if you want, you might keep your phones off so you can focus on the speakers and the slides. And if you wish to ask questions, just write them down in the chat box, which you should see on the right side of your screen. Be aware that this webinar is being recorded, and so that it will be possible to access it in the future. We send an email when the video is ready on the Bamboo YouTube page. So this is what is going to happen in the next hour and a half. After this introduction and a few polls for the audience, and one poll for the audience, Jorge Arroyo from Fundación Circe will introduce us to the Bamboo Project, to its objectives, to the technologies it proposes. Then we will go through another session of polls. And after that, Pedro Compais, who is also from Fundación Circe, will illustrate the topic of this webinar. So as you can see, it's combustion monitoring in the steel industry using computer vision and machine learning. We will close the webinar with questions from the audience, but as I said, you can send them before, and we might ask them during the presentations. Now, before delving into the topic of this webinar, as I said, we wish to ask a few questions through polls to you, to the audience, to learn a little bit about you. These polls will tell us more about you. The first one is about your expectations. So what do you expect from this webinar? Do you expect to learn more about standards or regulations, or about efficient technologies for your company, about projects of similar companies, or are you just here to network with companies and share similarities and solutions? So we will give you a few seconds to answer. These are the results. Most of you are here to learn about efficient technologies for your company, which is not surprising. Others are here to learn about projects of similar companies, and a minority are here to learn about standards and regulations and to network with companies and share similarities and solutions. Let's go through the second poll. So we are asking you to tell us in which kind of industry you work: paper, steel and iron, mineral, petrochemical, or other. So today, most of you are from another industry. We have 12% petrochemical and steel and iron, 8% paper, and 4% mineral industry. Last poll about you. So which is your role in your organization? Are you in R&D? Are you a technician? Are you in maintenance? Are you a manager, or are you something else? So most of you are in R&D. Second place, technician. Nobody is in maintenance. There are a few managers anyway, and there is a small percentage of other roles. So thank you for your participation, and now I will give the floor to the first panelist, Jorge Arroyo from Fundación CIRSE, who will tell us more about the Bamboo project. I asked the other panelists to keep their cameras and microphones off. So please, Jorge, tell us about this project.
Thank you, Selene, for the introduction, and good afternoon to everybody. Thank you for connecting to today's webinar. I am Jorge Arroyo, the technical coordinator of the Bamboo project, and together with my colleague Álvaro Bechamor Roman, who is the project manager, we are the heat coordinators. Bamboo is a European project funded in the H2020 Spirit Call. Its complete name is Boosting New Approaches for Flexibility Management by Optimizing Process of Gas and Waste Use. We are working in an innovation action. This is that we are reaching about tier 7 in our developments. It has been funded by the European Commission with more than 11,000 million euros. Bamboo ends in February 2023 after 54 months of work, and we are a consortium of 19 partners. As you can see, some of them are industries, and we are also research centers and small and medium companies. So we are a strong consortium. Most of you know the energy transition towards a secure and competitive energy system is a challenge for the intensive industries in the European Union. In this context, Bamboo is developing new technologies which will help to reduce the energy costs between 15 to 20%, reducing the greenhouse gas emissions until 23%, and improving the energy efficiency between 17 to 20%. In this sense, Bamboo project is aimed at demonstrating innovative technologies that can contribute to the industry, especially the intensive industry decarbonization, including which are the three main pillars of the project: waste heat recovery, electrical flexibility, and waste stream valorization. We are working on the demonstration of these technologies in 4 sectors: steel, petrochemical, minerals, pulp and paper sector. In Bamboo, we demonstrate technologies for waste heat recovery to valorize the waste stream which has a valuable energy content associated to their temperature, and reintroduce this energy in the process. During the project, we are demonstrating 2 technologies in 2 demonstrations in the steel sector and petrochemical sector. For the steel sector, we are working in high temperature heat pumps, which allow the upgrade of low to medium grade waste heat to higher temperatures. In this case, we are using the heat pump to generate steam from a residual stream of the process, reintroducing the steam on the process. This translates in a direct savings of energy, since part of the gas natural used to create this steam, to generate this steam, is replaced by the steam generated from the heat pump. In the second technology, contributes to the electric consumption reduction of the two-plus refinery. In this case, we are developing an ORC technology to recover medium-grade waste coming from a distillation unit to produce electricity, which can be consumed internally, so helps to reduce the consumption of the grid of the refinery. The second pillar, which is the electrical flexibility, includes technologies and operational strategies that will make possible that the industries take advantage of the lower electricity prices, and even they can provide grid services. And this technology enables the potential integration of renewable energy. Bamboo is working in applying this concept in the pulp and paper sector, with different strategies and technologies are implemented to allow the operation of a whole paper plant as a battery in the regional power grid. In this case, the concept means that during summer, where there is a high share of photovoltaic generation in the region where the plant is located, the plant will reduce or shut down their own generation system to consume power from the grid, while in winter mode, with very low renewable energy generation is expected, the system of the plant can be used not only for internal use, but also provide energy to the local power grid. Finally, the third pillar is the waste stream valorizations, that includes technologies and processes that allow the valorization and upgrading of different waste streams with a valuable calorific value. This stream can be generated inside the plant or outside the plant, and can be used as fuels in other processes. Here in Bamboo aims at demonstrating different technologies in the steel and mineral sector. For the steel sector, the concept is the increasing of the valorization of processed gases as fuels to increase the efficiency of the plant and reduce the fossil fuel consumption. In this sense, Bamboo applied two technologies that contribute to the valorization of this processed gas. And on the one hand, the CFD simulation allows analyzing the behavior of the combustion equipment when these processed gases are used, and on the second hand, a flame monitoring system to monitor the combustion for efficiency and emissions improvement, which is the main topic for today's webinar. For the mineral sector, the replacement of coke by biomass has been demonstrated with a direct impact on the fossil fuel consumption of the plant. Here again, the CFD simulation have an important role, and a multi-fuel low NOx burner has been developed, which allowing the introduction of biomass as fuel and reducing the consumption of pet coke and increasing the consumption of renewable fuel. This slide gives the expected impact of the Bamboo solutions based on the application to the 1% of the European energy-intensive industries of the different sectors. As you can see, there are important reduction in energy consumption, energy cost, and CO2 emissions, and the steel and iron has important weights in the industry of Europe, so the impacts are higher, but in the rest of the companies, there are important savings in these parameters. And finally, I wanted to remind you that this is the Bamboo Industry Month. As Helen explained before, we had 2 webinars related to waste heat recovery and fuel flexibility last weeks. I encourage to watch it since they are in the YouTube channel of the project. And we have two more webinars in the coming weeks together with today regarding the combustion monitoring. So I encourage you to subscribe to these webinars since they are I hope that they are of interest for you. So thank you again for connecting today.
Thanks a lot, Jorge. I have a question for you. These technologies are for heavy industries, which are also often highly polluting industry. So isn't there a risk that by developing these technologies, you actually encourage companies to develop even more these industries? Like, I mean, an alibi to keep investing while they should maybe switch to greener solutions?
I think in the case of the bamboo companies, they are or switching to more sustainable models. Even the Tupras, which is the petrochemical partner, is switching to other energies, like to other business models like the renewable electric generation or hydrogen production. But anyway, with the bamboo solutions, and the bamboo solution can be applied to those processes. For example, if you have a furnace which is currently fueled with natural gas, you have waste heat streams which can be recovered, for example, with heat pump or with oversea. But if you electrify this furnace, you will also have this waste stream. So you can apply the solution current and in the future, and even more. If you electrify the furnace, you can also apply some solution like electrical flexibility, which is not currently of interest because the consumption of the furnace is natural. So we guarantee of the solution for the present and for the future to make the processes of these industries more efficient.
Great, Jorge, thank you. Now, before getting into the topic of today's webinar, we will have another round of polls to understand your relationship with the technology we are going to talk about. So what do you know about artificial intelligence? Have you know about it from references in films, series, books, in real world uses? What do you know about its requirements and limitations, or about programming? You can select all that you know. So most of you know about artificial intelligence in real-world uses. That's good. A large minority knows it about references in films, series, books, etc. And a smaller part of you knows the requirements and limitations and about programming. Second question, so which are the uses of an advanced monitoring system for combustion, as far as you know? Here also you can select all that apply. Measure performance and or emissions, detect anomalies, or adjust operation parameters manually and or automatically. So for most of you, the main use is measure performance and or emissions, then adjust operation parameters manually and or automatically, and 53% consider that it's useful to detect anomalies. So Pedro, maybe I don't know if you want to give the answer, or if you want us to wait for the presentation to answer for it.
About the first poll has not wrong answer. It was about your knowledge about artificial intelligence. We see that some of you have knowledge about real world uses, also requirements and limitations, and the programming too, which is quite interesting to adapt the rest of the webinar. And yes, and regarding the second poll, well, I'm going to do an spoiler, and the right answers were all of them. So we will check them in a next slide. Yeah, I think that could be the review of the question and answers.
Okay, then I let you answer us. I let you make us discover this technology. I give you the floor, Pedro.
Okay, thank you. At the moment, you should see my PowerPoint, my presentation. Can you see it?
Yeah, I see a part of it.
Okay. One moment.
In the meantime, I remind the audience that they can ask questions. So on the right side of your screen, you should see a chat box, and you can write your questions there, and then we will ask the panelists.
Okay.
I'm sorry, but it's just a half of the presentation that I can see. I don't know if the other panelists can see it.
Yes, that's half of the slide.
Okay, one moment. And now?
Now, yes, now it's
okay, perfect. Thank you. Well, then I will start the presentation. Well, first of all, I've taken notes that a high number of you are coming from other industries than the steel industry. In this aspect, don't you worry about this presentation, because apart from the specific application for the steel industry, an important sections of this presentation are also focused on the general description of computer vision and machine learning, which can be applied to other industries. And one of the main challenges of Bamboo project regarding the combustion monitoring was the development of a methodology robust enough to be adapted between lab and semi-industrial scale. And I think all of this knowledge can be very helpful and interesting for all your cases, although you can come from other industries. Okay, and the last question before we start is this presentation will be about combustion monitoring in the steel industry using computer vision and machine learning. Just to keep in mind for the rest of the presentation, we could say that computer vision and machine learning are two subfields of the broader field of artificial intelligence. So, well, all of these concepts, artificial intelligence, computer vision, machine learning, are trending topics right now. And there may be some misunderstandings about them. So, in this webinar, we are talking about computer vision, machine learning. They are subfields of the artificial intelligence field. And in this webinar, we will talk in more detail about all of these, all of the definition of these subfields for the specific application of our project, and for these applications of combustion monitoring, which could be also extrapolated to a more process monitoring in other industries. Okay, that was a first notes that I want to make at the start. In this presentation, first, we will see use cases for the steel industry, which I think that it will be helpful to understand how this computer vision and machine learning can be applied not only to the steel industry, to other, in addition to other industries, because computer vision, machine learning, and artificial intelligence may be abstract concepts that may fail to come to a real world use. But with these use cases that we are going to check for the steel industry, I think that it will be clear for you. Then we will check the requirements for the implementation of this combustion monitoring solution. We will make a technology description of both the vision systems for furnaces and other we are focused on the steel industry, but this vision system that we are going to review could be also useful for reactors and other furnaces of other sectors as glass, ceramic, and so on. Later, we will discuss the results that we have achieved and the result that we are working at the moment within the Bamboo project. And after the results, we will see the next steps and finally the conclusions. Well, the first section, use cases. The Bamboo solution. Within Bamboo project, we have developed a monitoring system with image-based sensors to automatically evaluate combustion status. The block diagram, the flow chart of this system could be seen in this slide as we have a combustion process or any other process with a furnace or a reactor as the one shown in this image. Then we have image-based sensor which are related to the vision system. This image-based sensor provides us images, and with these images, we make an image processing which is related to the computer vision field to extract features. And these features are used to develop predictive models, which are related to the field of machine learning, to predict the combustion status of the furnace in this case. In this last image, we see one of the images of a semi-industrial furnace. Well, as I previously said, with the second poll, the uses for this solution, for this monitoring, are multiple. First, we can make a characterization of the operation. We can measure performance, anomalies, emissions of the furnace, the reactor, the process. All this information, well, first you can measure the quantitative variables as emissions or performance, And with these measures, you can detect anomalies in these variables. So you can you can stay alert and detect dynamic changes on these variables and act in consequence. And all of this information, their objective is to adjust the operation of the process to optimize it according to the additional information that is being measured by the monitoring system. And by adjusting the operation, you can optimize it with the both approaches of control. All the information measured by the monitoring system could be used by a human worker to manually adapt the operation parameters of the process, but also could be included in a closed loop control to automatically adjust the operation of the furnace or the reactor, or as the industry would want. The challenges to address in the Bamboo project are the standardization of the methodology, which is the case adaptation. As we have said, we have worked on both on laboratory and semi-industrial scale, and the methodology needs to be robust enough to adapt the results and the monitoring system to the different stages of development, and also to be adapted to other cases that they study. In the steel industry, you may have several furnaces along the whole steelmaking process, and an important point is to develop a monitoring system that can be easily adapted to each one of them. And if this monitoring system can be adapted to other industries as glass, ceramic, cement, or so on, is another challenge to address that we have worked within the Bamboo project. And the last challenge is the pioneer application for steel factories, which we will see in a next slide. So the benefits of the Bamboo solution: by optimizing the operation of the process, we obtain energy savings, which can be, for example, related to the reduction of fuel consumption, but also with the reduction of downtimes of the operations, and another more cases. There are plenty of cases in which all of this additional information that the monitoring system is providing can provide these energy savings. And also it benefits for the emission reduction, which is more related to the aspect of environmental taxes of the use of these furnaces and technologies. And the main cause of the solution are the hardware, which we could say the vision system, the image-based sensors. Also, there are installation within the facility, within the industry. And in the end, the software development, more related to the image processing and development of predictive models. And within the steel industry, as I previously talked about, the challenge of a pioneer application in the steel industry is that we have worked in the Bamboo project with challenging combustion conditions. We are in the case of blast furnace gas co-firing. For you of some of you may don't know which implies this case. I will summarize for you. Blast furnace gas is a waste stream generated in the steel industry, and it has a low calorific value, but it can be valorized as fuel to reduce the consumption of other fuels as natural gas. So we are reducing the consumption of natural gas by using blast furnace, but Which is the problem? Well, as I said, blast furnace gas is a waste stream. It's not a common or conventional fuel. It doesn't provide as many energy as natural gas, and related to this, its combustion is more unstable. So it's more challenging to monitor. And also, the pioneer application of the steel industry is for the monitoring of multiple burners, as the one seen in the image of this slide, which is an image for a reheating furnace. These furnaces have several burners, and common sensors to monitor this combustion can only measure the performance, the emissions for the overall furnace, but you don't know if some of these burners are not working properly or has a malfunction. Well, by using the monitoring system developed within Bamboo project, which uses image-based sensors, as seen in this image, all of the burners can be seen with an image, and you can see the different flames of each burner. And with this, the monitoring solution of Bamboo project could monitor each one of these burners to detect which of them will have the malfunction. So you don't need to check any one of them to check the operation of the furnace. And moving on, as I previously commented, there are several steps of the steel making process which can use this monitoring system. Well, in this project, we have studied in more detail the case of reheating furnaces, but in the steel making process, you have several furnaces, as the ladle furnace and also the blast furnace. And even for the electric arc furnace, there are vision systems that can be installed to monitor their operation. Okay, moving on, we will see the requirements for implementation. Well, first, to monitor a furnace with this vision system, we will need a viewing port. So the inside of the furnace could be seen by the vision system. And this vision system has different requirements. First, its sensibility, which light range we want to measure, because depending on the light range, you will see different things. Second, the field of view. Depending on where the vision system is placed, different parts of the furnace inside can be seen. And it depends on which parts of the furnace you want to monitor. And depending on the field of view, there is also the component of the lens which may define this field of view. With the definition of the placement for the vision system, you will have to answer other questions, as the protection and cooling that the vision system needs, because the vision system can be implemented outside the furnace or inside the furnace. But as you can think, it's not the same to have a vision system on the outside or in the inside. The operation temperature will be different, and different protection and cooling will be required. And also the size of the vision system, because if you want to introduce the vision system through a viewing port, the proof diameter should be lower than the viewing port, and also the proof length should be high enough to cross all the wall depth, because because if the proof length hasn't a sufficient length, hasn't a sufficient value, part of the image will be covered by the viewing port, by the inside of the viewing port, and you will lose part of the vision of the furnace inside. Okay, moving on to the next section, the technology description. In this section, we are going to review three main blocks. First, the vision systems, the hardware. Next, we will move towards the computer vision field. And next, to the machine learning field. And in the end, we will check the implementation of both computer vision and machine learning in the same application. So, first of all, vision system for combustion monitoring. Well, the first aspect for the vision systems are the cameras. We have different types of cameras, and this is related to the previous aspect of the sensibility. We have, on one hand, the visible or color cameras, which acquires images as seen by human eye. We also have infrared cameras, which can measure temperature. And we also have ultraviolet cameras and also other type of cameras as hyperspectral and so on, but they are less established on industrial scale. As I previously commented, in this slide we are seeing different vision systems for different placements. The first one of the leftmost image is a system for an external placement. Next, we have an internal system which is introduced through a viewing port. And the last image is also for an internal vision system which is introduced through the viewing port, but in contrast with the previous one, this vision system can be removed from the inside and introduced again. And for that purpose, it has a transfer device to extract, to remove the vision system from the furnace inside in case of malfunction of the vision system or for other cases. Well, as you can see, these vision systems are complex systems. They have several devices, and they also have auxiliary equipment. They are not only a simple camera. Well, these systems are industrial systems. They are being sold by different companies, and as an industrial equipment, they have different devices to guarantee their operation. You have the cooling, which can be made with water or air. You have the transfer device, a control unit purging air for the shutter box and the lens of the camera. And you also have all the data acquisition system to capture the images from the camera and communicate them to the computer or your control system in your plant. Okay, so for the next block, computer vision, we could summarize computer vision as the techniques to perform complex tasks with a visual component, as for example, thresholding, equalization, and edge detection. Common solutions of computer vision may be split into 5 subtasks. First, we have the step of image acquisition. Then we have pre-processing, where images acquired by the system are transformed with some preliminary operation. For example, with this image, we could crop the image and remove the sides of the image because, for example, they do not provide us the information that we want. Next, we have the step of segmentation. In this case, the segmentation would be more related, for example, to the segmentation of the flame, which is the area that I'm remarking in the image. is the selection of this area in the image. With computer vision may have, well, in this case have several algorithms to automatically detect the flame within the image. Once we know which are the flame pixels, we can go to the step of future extraction, where the information of all these flame pixels can be translated to another set of variables, like, for example, in this case, flame geometry. For example, which is the area of the flame, which is its length, its width, and in the end, we have the step of interpretation. We will have the length, the width, for example, of the flame, but how does it translate to our system, to our process, which are their translation to our process variables? For example, in this case, we could translate flame geometry, flame length, to, for example, the event of a malfunction or the extinction of the flame, for example. Okay, and for the next step, machine learning, we could say that machine learning are the techniques to perform complex modeling based on sample data, as for example, classification. For example, if you have a cloud of points and each point is related to a specific class, you can develop models for this classification. Also, you can make regressions to adapt also point clouds to extract to specific functions of these clouds and understand how the process is operating, and also anomaly detection. As a computer vision, well, in this case, machine learning could be split into 4 subtasks. First, the first one will be the data acquisition with the measure of the process variables from tests. Next, we will have pre-processing, where we could, for example, remove missing or wrong measures from the sensors. Next, we will have the future extraction. For example, at this point, we will have a huge amount of data from the process, but we don't know how to manage, how to extract insights from this huge amount of data. Well, machine learning have techniques to select the more relevant process variables to tackle all of this huge amount of data and extract only the key important information for you. And in the end, we have the step of modeling, which is more related with the development of predictive models, with the, for example, with this huge amount of data, the possibility of predict one of the variables with the rest, and so on. At this moment, this can be seen abstract, but in the next sections of this presentation, we will go in more detail with this application. And last, how could be the implementation of computer vision and machine learning? Well, in this case, these techniques could perform complex tasks with a visual component and also a modeling based on simple data. And with these techniques, we could make application as digit classifiers, the object detection of the pose estimation. As you can see with previous examples, more complex challenges can be addressed by joining computer vision and machine learning. And how can we join them? Well, in the previous example, for example, we have the system, the furnace, and the computer vision will acquire images and process them to extract image information and or characteristics. And this image information and or characteristics will feed the machine learning step. And the machine learning step will develop, for example, the prediction of process variable using also process variables measured in the system as temperatures, pressure, or so on, and also images from the process. Okay, now we are going to focus on the results of the Bamboo project, which, as you can see, you will see that they are focused on a case of the steel industry, but they can be extrapolated to other industries, at least in terms of methodology, and to understand how computer vision and machine learning can be used to optimize process in general. So I think this could be also very useful for you. Okay, the Bamboo solution. To remind what we have previously said, the Bamboo solution is a monitoring system with image-based sensors to automatically evaluate combustion status. We have developed it for a use case of production furnaces in the steel industry, testing fuel blends with natural gas and blast furnace gas. And the whole project for the flame monitoring could be summarized in this flowchart. First, we have a step of definition of requirements. Next, we move towards the development of the diagnosis model and also the engineering of the monitoring system and installation of the monitoring system. This means the commissioning of the vision system and the analysis of the commissioning and installation of the monitoring system. And last, we have the real demonstration where we are here close to the end. So as you could see in the next results. First, in the step of definition of requirements, we have made an experimental campaign on a semi-industrial scale. This is the furnace on semi-industrial scale. It has 1.2 megawatts and it has a size of 5 by 2 by 3 meters. And in the right, you can see an scheme for the furnace. We tested 3 optical devices, a color camera, which is this one, an ultraviolet camera, and a spectrometer. In this phase, we defined the requirements for the monitoring system, and the color camera was proof as sensor of fuel blend, oxygen, and nitrogen oxide concentrations in flue gases. And we have published these results in a previous conference. These are one of the images that we can see with the color image. This is the furnace inside, and since we deploy this camera outside the furnace with a temporal assembly, this camera is not an industrial vision system. We set a tripod, and we take images with this camera. And all of this black area is the part from the furnace that can be seen due to the placement of the camera outside of the furnace, in this step at least. Well, for the step of the development of a diagnosis model, we make an experimental campaign on lab scale. This is the scheme of our facilities in Circe. We have a 20 kilowatts burner, which have a lower size than the previous semi-industrial furnace. And we also tested 3 optical sensors, the color camera, which was the same, the ultraviolet camera, and the spectrometer. And the combustion was characterized, and optical devices were also proof as sensor for fuel blend and air-fuel ratio. We also published this result in a previous paper, so you can check them. And here we can see, in this case, an image from the color camera and an image from the ultraviolet camera.
Pedro, sorry,
yeah.
if I can interrupt you, we have a question. Which features have been extracted from the flame images to characterize the combustion conditions? Sorry.
Yeah, okay. Yeah, in this case, the image features that were extracted, well, we made a literature review of previous developments in the not only in the steel industry but in other industries for other applications, and characteristics for combustion could be summarized in 3 types, which are statistical features, geometric features, and texture features. We extract features from all these types from the images to have a complete characterization of the flames. Well, in this is an interesting aspect to discuss in more detail in more detail in other webinar. But well, there is a lot of features to use. You may see that different researchers use a specific set of them. Well, there is a lot of knowledge in this aspect, and it's very interesting. So to summarize, we use statistical, geometric, and texture features from the flames to detect these changes on the flames for the fuel blend and also the air fuel ratio. Okay, so some more results. We developed code to process the flame images and adjust the predictive models of the combustion conditions. Slight variations were hardly perceived by the human eye. In these images, the only change between these flames are the addition of blast furnace gas, and well, maybe you can see it with the human eye, maybe using glasses or increasing the brightness of your monitor, but this is not the worst case scenario. And what is the problem? You are going to look all of these flames 24/7 to detect if these changes are taking place. Well, it can be a complex and challenging task. So although with these images the variation can be hardly perceived by the human eye, in this graph, for example, the y-axis is one of the features extracted from the images, and you can see that by changing the fuel blend, which is the different colors, there are a clear tendency, there are clear changes on these characteristics, and you can count on them to detect these changes. And in the end, we only using these images, we could well, we can predict the air fuel ratio of the process, which is a very important aspect, and it's a very important aspect. And well, we will see their importance for other applications. And finally, in the step that we are at the moment is the real demonstration. Another experimental campaign was made on semi-industrial scale. We come back to the semi-industrial furnace to demonstrate the system that we have developed at lab scale. And we use a vision system for combustion monitoring with a color camera, and now we can acquire these images. At this phase, there is an industrial vision system. We don't have the preliminary assembly of our camera with a tripod. Now we have an industrial vision system with cooling and protection devices. And by introducing this vision system in the furnace inside, you can see all the furnace inside and increase the quality of the images. We write code to calibrate the predictive model from lab scale on semi-industrial scale, and a very good result that we have achieved is that the lab scale were repeated on semi-industrial scale. We have also detected the slight variations which are hardly perceived by human eye, and also we have achieved an online prediction of air-fuel ratio using color images without optimizing the code, because that wasn't the main challenge of the main scope of this project. We achieved 3 predictions per second, so we can process 3 images per second and provide free predictions of their conditions, their combustion conditions, to monitor the furnace, which I don't know if in your industries, but maybe you are, I don't know, depending on the scope of your monitoring. Maybe you are using seconds to monitor, maybe minutes, or a couple of minutes, or so on. Okay, just to
So
close.
Pedro, sorry.
Yeah.
Another question. Yeah. Which machine learning algorithm have been tested for the development of the predictive models? Does the algorithm selection affect the results?
Okay, well, within Bamboo project, the approach that we have followed, since one of the challenges was the standardization of the methodology, within Bamboo project, we have checked different kinds of machine learning algorithms to test their performance and check which one of them is the better alternative for our case. And in this case, we are also curious about the power and the requirements of each machine learning algorithm. In this case, we could summarize in 3 types of algorithms. One which was very simple, for example, a logistic regression, which is a very simple algorithm, which also tested an algorithm which could be more in the middle of the range of alternatives, which are support vector machines. And also we tested artificial neural networks, which are more related to deep learning. And we checked that with all the algorithms, the behavior was quite similar. Well, in this case, we also take a lot of consideration and effort to address overfitting, and in this aspect, maybe the results of artificial neural networks don't provide overly optimistic results, which in other researches you may face these overly optimistic results. And since in our research, at least, we tackle this problem of overfitting, we're checking several metrics, and the model doesn't suffer for overfitting, and the results were similar from all the machine learning algorithms. Well, this is important because if you plan to make these predictive models, well, artificial neural networks may be the more powerful technique, but if you want to implement or develop these algorithms, you will need the required equipment from it. For example, a GPU, a graphical processing unit, and training times may be also longer. So we wanted to check different alternatives of different kind. Well, the results were quite good and promising, and they were repeated for both lab and semi-industrial. And yeah, at least we were talking about, well, yeah, the results weren't affected weren't affected too much by the use of the different machine learning algorithms. We were on from 80 to 99% of accuracy depending on the combustion conditions, because some of the combustion conditions can be more challenging than others. And that was similar results for all the machine learning, at least in these cases, in this application. Okay, so to end this section, you can see that the development of the bamboo system has been complex, because although vision system and experimental tests share characteristics, images may differ significantly. In these images, you can see in the step of definition of requirements, we were acquiring these images, and we can detect variations in these images which were related to the process conditions. We develop a diagnosis model at lab scale using these other images. In these images, you are seeing the flame from the front, but in these images, you are seeing from the side, which may be a more conventional placement of the camera regarding the flame, at least for research studies. and you can see that the differences between the images are significantly. And also you can see, yeah, you have developed a model for laboratory with these images, but you have these images on semi-industrial scale. How is the predictive model going to work with these images? I'm not sure about how this laboratory model can be adapted to semi-industrial scale. There is so much difference, but we use the same methodology that in the lab scale, and we use all the knowledge of the lab scale, and using the same set of image features, we can adapt the predictive models of the lab scale to the semi-industrial scale, and we could predict we can develop the predictive models and monitor the combustion conditions for these images too. So to summarize, the methods that we have developed were robust enough to repeat the results for different cameras, for different vision system, and for the different scales. In this case, this is lab scale with a research camera which does not have protection or cooling, and this image, this is semi-industrial scale, and we are using an industrial vision system with cooling and protection devices. Okay, that was for the section of the results. Now we are going to check the next steps of the Bamboo project. And the next step will be the industrial scale. In the Bamboo project, we have we plan to finish for semi-industrial scale with this semi-industrial furnace with only one burner. And at least from my side, I will be happy to test this on industrial scale and test these furnaces with multiple burners to detect the to detect, to monitor the operation of each one of these burners, which can't be currently monitored but other common sensors. So this would be a higher advance of the state of the art towards this application. And also other aspects for the next steps are the real time. Real time is a term which can be related in the origin to computer science and can be related to milliseconds, to the processing of information within milliseconds. So as I previously said, we process images within seconds, not milliseconds. So this processing could be adapted and the predictive models too to achieve these real-time requirements, which has not been the main scope or challenge of the Bamboo project. And also you have the field of deep learning. Some of you may know that deep learning is other of the trending topic right now. Deep learning is another field of artificial intelligence, and in particular, is a subfield of machine learning, which is more related to with more powerful models and a processing of the information that may not need the extraction or a specific features for each case. So a new methodology can be developed to implement these techniques of deep learning. And in this aspect, there is another project, the project Retrofit, which is at the moment under development, with this addressing the real-time monitoring in the cement and ceramic industry using computer vision and deep learning. Since the high number of assistants from other industries, I recommend you to check this project, because Circe, we are working on this project too, in the aspect of this real-time monitoring with computer vision and deep learning. And well, we're working on it too. This project is not so close to the finish line as Bamboo project, but I think that maybe it's halfway the project or even more advanced. So there is quite work done, and it's very interesting too for these other industries and as next steps of Bamboo project. Okay, so at this moment we are in the section of conclusion. Within Bamboo project, a monitoring system has been developed with image-based sensors to automatically evaluate combustion status. The development focuses on production furnaces in the steel industry, testing fuel blends with natural gas and blast furnace gas. The monitoring system aims to increase energy savings and reduce emissions by providing additional information to adjust the furnace operation. The results that we have achieved could be summarized in the following ones. First, we have predicted air-fuel ratio of combustion using images. An online processing has been achieved with 3 images per second without a code optimization. We have perceived with our combustion monitoring system slight variations which can't be perceived by the human eye, and the methods developed have been robust enough to repeat results on lab scale and also semi-industrial scale, despite system differences. This monitoring system has overcome its challenges, which were that the methods developed have been robust enough for their implementation with different system and scales, repeating results on lab scale and semi-industrial scale. And also for the novel application for the steel industry, we have addressed the particular combustion behavior of blast furnace gas co-firing, with blast furnace gas being a waste stream. So you have a waste stream which is not a common fuel, and you are burning this fuel, this waste, and it has a more unstable combustion, which can be the flame can be extinct or turn off more quickly, and it's an alternative fuel, and all of the bamboo solution has addressed the valorization of this blast furnace gas also. And finally, the bamboo solution to end is a promising alternative to control industrial furnaces with multiple burners, for which traditional sensors do not provide measures of each specific burner. And okay, that was all from my side. Thank you all of you for your attention. And I don't know if there is any question, or we can delve in more detail in some section of the webinar, or well, as you want. Thank you.
Thank you, Pedro. There are no questions for now, but if someone wants to ask questions, there are still a few minutes. What I wanted to ask you is actually, how does this technology, how is this technology good for the environment? I mean, the whole point of the bamboo project is to, to assess, to address issues of energy, etc. So how does this benefit the environment?
Yeah, this is a more complex case, because with this technology, we are not talking about a new type of burner that enables the combustion of a waste stream and enable the a direct reduction of natural gas, in the sense that, well, as in previously webinars of Bamboo Project, you can see novel burners or alternative for combustion, and you can see that, well, with this new technology, you can reduce the consumption of natural gas a 5%, or I don't know, I'm making up the numbers. And with this reduction, you don't purchase this natural gas, and you are valorizing a waste that won't have a use to reduce the cost and the environmental footprint of your process. In this case, coming back to monitoring, to combustion monitoring, well, for example, in this semi-industrial furnace, you are using the blast furnace gas. You are already valorizing this waste stream and reducing the carbon footprint, which is the aim, the scope of this monitoring system. Well, as I say, you can valorize this waste stream, but its valorization, its combustion cannot be optimized, because it is unstable. And for example, these flames, this burner can move towards suboptimal conditions, where the efficiency of the furnace, of the process, can be reduced. So with this monitoring system, you aim to increase the quality, the capacity of the monitoring to detect these small changes and correct early these malfunctions or suboptimal conditions. So in the end, you will also reduce you will contribute to the reduction of the of the of the consumption of the whole process, because you are optimizing in more detail the process, but to define all of this in a high level of detail, you will also need to know, for example, which are the downtimes, the stop times of your process. For example, if you don't have this monitoring system, for example, how many problems do you have of malfunction in your burner? And for example, with this malfunction, hot spots in the furnace can occur. And for example, the furnace can be some component of the furnace can be damaged from this lack of monitoring. How many of these malfunction of these stop times are you having? And once we know all of this information, we could also say, well, but if you have this combustion monitoring system, all of these changes can be detected earlier, and these malfunctions can be monitored early and fast, so the damage and the problems and the time working on suboptimal conditions are reduced. And in the end, all of this will work towards the optimization of the efficiency of the process. But as I say, it's not so direct as in the, for example, the case of the novel technology burner. It's more it's more related to the monitoring of suboptimal conditions.
So you're
Yeah,
telling us that there is a synergy between the different project, the different technologies in the bamboo project.
Not for example, but they are complementary. I could think, for example, because for example, well, here in Circe, we have also developed part of the simulations of the computer fluid dynamic simulations of the furnace, and well, they are interesting to have a previous preliminary insight of the working of the process of the furnace, but apart from the design and the adjustment of specific cases to optimize the conditions, you have um, you have the operation of an industry 24/7. In this operation, in the day by day of industries, you may face that the simulations provide a very important insight, but you also need sensors. You also need measures to have to know how is working your process, and to check if for example, the results, the case is simulated for these novel burners or with these simulations are being correlated with the measures of real sensors in the 24/7 operation of the industry. A lot of problems may arise, and you need new information of your process to understand if there is some changes. These processes may change by a lot of of events and conditions.
I think it's clear. We have a question.
Yeah.
Can visual information be used to adjust the excess air ratio when we compare to oxygen sensor? Why should we prefer this visual measurement system instead of oxygen sensors?
Could you please repeat the specific variable? That would be, well, the question. The
first
question
part is, can this visual information be used to adjust excess air ratio? And when we compare to oxygen sensor, why should we prefer this visual measurement system instead of oxygen sensor?
Yeah, totally related to our webinar. Excess air is related to this parameter, the air fuel ratio. So, air fuel ratio can be, more than 1 for over stoichiometric condition, which could be related with excess air, and lower than 1 for conditions with lack of air. So we have tackled this specific question in the project, and we have used these cameras to detect these changes, both in lab scale and semi-industrial scale. And for example, this is one of the examples. In this graph, for example, you can see that in this from 1.0 to 2.0, you will have excess air. Going towards 2.0, you will have more excess air. And for example, you can see that excess air.
There's another.
Okay. I will summarize. It can be very correlated. We have correlated it at lab scale, but also at semi-industrial scale. Please see our publication in this conference, and when to use camera and when to use traditional sensor. As I say in this slide, oxygen sensors for furnaces with multiple burners cannot measure the specific behavior of each burner. They only measure the overall behavior of the furnace. So the camera will provide an additional, a higher added value because it could detect these changes on each one of these burners. Yeah, that was. And the following question was? I think it was another question.
Sorry, I had my my microphone muted. It was, can this visual information be used to adjust excess air ratio? And when we compare to oxygen sensor, why should we prefer these visual measurement systems instead of oxygen sensors?
Yeah, okay. I have answered this question. I thought that you were saying that was another question. Okay.
It's one question. Anyway, we are at the end of this webinar, so it's 4:29. So our webinar ends here. I hope you enjoyed it, and I thank our participants and panelists for being with us. I remind you that the next webinar of the series will take place next Wednesday, November 23, at the same time, 3 p.m. Central European Time. And in that occasion, we will talk about high temporary heat pumps and steam generation. So I hope to see you there, and I wish you a great afternoon. Goodbye.
Thank you. Bye.
Thank you. Goodbye.